Hey guys, it's Miss Maneely, and I'm going to give you a quick lesson on inference for two-way tables. In our last lesson, we looked at inference for one-way tables, or often data that is distributed and described by a list, and we used what is called the chi-squared goodness of fit test, where basically we were looking at one variable, and instead of just paying attention to successes and failures, we were looking at this variable over many different categories or many different values of the variable, and we were comparing that distribution to some claim about the population. And to do that, we do what is called a chi-squared test for goodness of fit. The type of tests that we're going to be looking at today are going to give us two other scenarios. One would be looking at the relationship between two variables, and the other would be looking at the relationship of one variable but comparing two distributions. So perhaps I want to look at how students performed in different math tests at Southern and compare those performances to students at South River, for example. So I'm looking at one variable in terms of the test scores, or maybe we could be looking at the number of passing or meeting the standard at Southern versus South River. But I'm looking at one variable and I'm comparing it, the distribution of that variable over two different populations. And in both of those situations, I would be displaying the data in a two-way table. So anytime you have a two-way table of categorical data, we can compute or we can perform a chi-squared test on that data. So as an introduction, we know that a two-sample Z procedure from Chapter 10 allows us to compare the proportions of successes in two populations or for two treatments. But if we want to compare more than two samples or groups, or more generally, what about if we want to compare the distribution of a single categorical variable across several populations or treatments? We need a new statistical test. And the test starts by presenting the data in, like I said, a two-way table. Two-way tables have more general uses than comparing distributions of a single categorical variable. They can also be used to describe relationships between any two categorical variables. So the problem of how to do many comparisons at once with an overall measure of confidence in our conclusions is common in statistics. This is the problem of multiple comparisons. So statistical methods for dealing with these kind of multiple comparisons usually have two parts, where we look at an overall test to see if there's a difference to begin with. If there's not, or if we don't have evidence of a difference, then we're kind of done. But if there is an evidence of a difference, then we have to look a little bit closer and figure out where that difference is occurring. So just to kind of give you an example, maybe I want to see if there is a difference in the distribution of students who are successful in different grades in different departments, for example. So maybe I'm looking at, math and English and science and social studies. And I'm looking at this like 9th graders and 10th graders and 11th graders and 12th graders, and maybe I'm looking at the number of students who have failed these subjects in one semester. So maybe I've got some numbers here. I'm just making this stuff up. Anyway, I'm just making these up. But you can see that we have a difference here. Now, obviously, my groups of individuals are going to be of different sizes, so I can expect there are going to be difference in counts. But what we want to know is if that difference is indicative of like a true difference between the groups. But in this case, because I've got so much going on, I can't do a single test for proportions or a single sample test for means. I can't even do a difference between two because I've got so much going on here. And because I'm dealing with counts of successes, and in this case I'm dealing with a lot of different types of successes, I need a new test. And so what the chi-square test will do is it'll look to see if there is a difference, a significant difference somewhere in my data. Now, it doesn't tell me where that difference occurs, so that's what the follow-up analysis requires us to do. We're going to be focusing, though, on the overall test and understanding how to perform a chi-square test, and then we'll talk about the follow-up analysis a little bit later. Okay, so there are essentially three types of chi-square tests. We've got the goodness of fit test, and usually with a goodness of fit test, you can you can label your data or organize your data in a one-way table or in a list. And what the goodness of fit does is it compares the distribution of a single categorical variable for one population, and it compares that distribution to some claim. So this would be like when we have the Mars, the M&M company, published its distribution of colors, and then we open up a bag of M&Ms and we see if the distribution of colors in that bag is consistent with what the company claims it should be. This is what we call a goodness of fit test, or a test for goodness of fit, where we have one variable with many subcategories or with many values and one population. Okay? The next two types of tests are the types of tests that we're going to focus on today, and both of them involve two-way tables. And so on the surface, sometimes these two tests look very, very similar. And again, they focus on organizing the data in two-way tables. So when we look at the data, we have to ask ourselves a couple questions. First of all, how many variables are we looking at, and how many groups or how many populations are we comparing? So in this first situation, this is called the test of homogeneity. It compares the distribution of a single categorical variable. So again, it's one variable, but it's comparing it over many populations. And so it's important to recognize that. The other type of situation is actually what we call the test of independence. And the test of independence is actually where we're comparing two variables. So it's one group, and it's one group that's being labeled in two different ways. So maybe I'm looking at a population of students and I'm labeling them by their gender and again by whether or not they're going to prom. And so that would be, I would present that information in a two-way table, and I would use a chi-square test for independence to see if there was an association between those two variables. So the way the data is presented often looks the same, so you do have to be able to differentiate between the two. The only real difference in these tests is how you set up your null and alternative hypothesis, and obviously that's going to affect what your conclusion is. The math for these two set tests are identical. So you're not really doing the math any differently. So let's talk about the test for homogeneity. Again, this is one variable and several different populations. So maybe I'm looking at the distribution of regular chocolate M&Ms and comparing it to the distribution of peanut M&Ms or pretzel M&Ms to see if the color distributions are the same. And so our null hypothesis, and again with the chi-square test, we often write our null and alternative hypothesis in words. And so the null hypothesis would be that there is no difference in the distribution of the categorical variable for the several populations or treatments. Now obviously you'd be putting this in context. So if I was using the M&M distribution example, I would say there is no difference in the distribution of colors of plain and peanut M&Ms. My alternative would be that there is a difference. And notice that I'm not worried about upper tail or lower tail. I am just trying to see if there is a difference somewhere in these two distributions. So we compare the observed counts in a two-way table with the counts that we would expect if the null hypothesis is true. So this is the same step that we would take with the goodness of fit, except it's a little bit more complicated. So let's take a look at an example. So it says, modern technology changed the distribution of birthdays. With more babies being delivered by planned C-section, Mrs. McDonald's statistics class hypothesized that the day of the week distribution for births would be different for people born after 1993 compared to people born before 1980. After all, why would a doctor plan a C-section for the weekend? To investigate, they selected a random sample of people from each age category and recorded the day of the week on which they were born. The results are shown in the table. So if you look just at the numbers in the table, we've got the distribution of birthdays before 1980 and then the distribution of birthdays after 1980. Our sample sizes are relatively similar, 177, 173, and you can see that there are definitely some differences in the distribution. So for example, Sunday seemed to be like a pretty popular birthday for people born before 1980, but not so much after 1993. We see a big difference here, too, on Thursdays. It looks like people born after 1993 prefer to have their, or parents of children born after 1993 tend to prefer to have their children born on a Thursday. So we can see that there are some differences here, but again, we ask the question, like, are those differences due to natural variation, or is this evidence that these distributions really are different and that the distribution of birth, or that C-sections have really changed the distribution of birthdays? So we want to go ahead and perform a test. So we want to state the null and alternative hypothesis. So again, in words, I would state my null hypothesis. There is no difference in the distribution of birthdays for people born before 1980 and after 1993. And then my alternative would be, there is a difference in the distribution of these two groups. Okay. We will be computing the chi-squared test statistic the same way we did before, where we take all our observed counts, we subtract our expected counts, and we square that, and then we divide by the expected count and add them all up. However, when we're doing it with a two-way table, coming up with our expected counts is a little bit more complicated. Because if you remember when we were looking at a goodness of fit, we had some distribution for the population that we were comparing it to. So we had some understanding of what we expected our outcomes to be. With a two-way table, it's a little bit more complicated. And the way we determine all of the expected counts is to take the row total times the column total and divide by the table total. And I'll show you what I mean. Okay, so if we go back and we fill in the expected counts now. And actually, let me see if I can get both graphs on the same page. Hang on one sec. Okay, so I just pasted my observed counts. So these are my observed counts. And to determine the expected counts, remember we take the row total times the column total. Oops. And we divide by the table total. So this is kind of a tedious process. So if I wanted to determine the number of people born before 1980 that were born on a Sunday, I'm going to look at the corresponding cell in my other table. And I'm going to look at my row total, which is 21, and my column total, which is 77. And so what I would do to get that value is I would do 21 times 77, and I would divide by my table total of 150. You can see this is sort of tedious. If I wanted to find this value, I would have to do 21 times my column total, which is 73, and divide by 150. And so what I'd like you to do is press pause, and I'd like you to go ahead and complete this table and fill in all of the values that we would expect to see if our null hypothesis is true. And if you filled it out correctly, that's what you should see. And so if you think about what we would have to do now to compute my chi-squared test statistic, remember we said that chi-squared is equal to the sum of the observed minus the expected squared over the expected. And so what I would need to do is for every single cell, so in order to compute this, I would have to do, for example, if I'm looking at this first cell, I'd have to do 12 minus 10.78. I'm going to square it, and then I've got to divide by my expected value of 10.78. And then I would add that to the next cell. And it wouldn't actually matter what order I went in, but if I went down to this particular cell, those born before 1980 on a Monday, I'd have to look at 12 minus 11.807. It's painful even showing you this, divided by my expected again, which is 11.807. So you can imagine trying to do this by hand. The nice thing is your calculator actually has a place where you can enter two-way tables. Some of you, if you've taken pre-calculus, hopefully you guys have learned how to utilize the matrix functions of your calculator. If you haven't, that's okay. We're not going to do a lot with the matrices. We're simply just going to enter our data into a matrix and then allow the calculator process to go ahead and utilize the matrices the way it is fed. But basically, a matrix is just a two-way table, or actually it could be a three-way table. It could be a 3 by 5, but basically we have different rows and different columns that we can enter into the calculator, and we can perform mathematical operations with matrices. We can add them, subtract them, we can multiply them. There's lots of different uses for the matrix, and one of the ones is going to be to help us determine the chi-square test statistic. So what I basically want to do is enter in all of my observed counts in the matrix. So the way we go to the matrix, and you should see it, it's above my X inverse button, so it's below the math key. You're going to have to hit the second button first and then hit matrix, and you're going to see this screen. Now, if you want to enter data into a matrix, you must scroll over to where it says Edit. And once you're in the Edit mode, you can choose the matrix that you want to change, and then you can add in all of your values. So I'm just going to go ahead and utilize matrix A. You have to enter in the dimensions of your matrix. And if you remember, the dimensions of the matrix are always row by column. That's your dimensions of your matrix. And so if I look at my table of observed counts, I'm not going to worry about the total, but I can see the number of rows. That would be 7 because there are 7 days in the week. And then my number of columns would be 2. I'm dealing with 2 different populations of people. And then I'm simply going to enter in my observed count. So these are the whole numbers. So I've got 12. And when you press enter, it's going to go across. You do want to make sure that you put everything in the correct order. So go ahead and take a minute to enter the data into your matrix. Okay, and once you've got everything in there, the nice thing is your calculator will actually compute the expected values for you. So you don't actually have to go through the process that we went through of creating that expected count matrix. So let's go ahead and talk about the conditions that we need for inference. And they're really the same conditions that we had for the goodness of fit test as well. You want to make sure that your data comes from either a random sample or a randomized experiment. And also, because with a test of homogeneity, we're dealing with 2 samples or more than one population, so 2 or more groups, you must make sure that you include the independence condition. The independence condition isn't needed for the goodness of fit test, and it's not needed for the test for independence, which I know sounds kind of funny. We need to establish independence anytime you're dealing with more than one group that you're comparing. The 10% condition is the same as before. Whenever we're sampling without replacement, we want to make sure that our population is at least 10 times our sample. And the large counts, this refers back again to our expected counts. Now, I've entered in my observed counts. We don't know what the expected counts are yet, so we have to figure that out. We need to make sure that they're greater than 5. Now, actually, we did figure it out. We figured them out by hand, didn't we? So we figured out the expected counts, and when you look at that table, you can see that all of those values are greater than 5. Now, one of the things you will need to do is write down your expected counts. And like I said, I'm going to show you how to do that using the matrices, so you'll be able to just get that off of your calculator, so it'll be a little less tedious. But you do need to write them down, and you do need to share that, you know, the all expected counts are greater than 5. So in this case, if you think about it, we were looking at random samples of individuals from the 2 different groups. I believe it said in the problem. If we look back at that problem. It says, let's see, after all, why would we to investigate? They selected a random sample of people from each age category. So we know we have random selection from both groups. Okay, so that's met, right? So random selection from both groups. We had one group had 77 people in it. So we know that the population, if I say N of 1980, was 77, and I know that that population is greater. Whoops. So if I'm looking at my population my population for 1980, I know my population for 1980 is going to be greater than or equal to 770, and I know my population for 93 is going to be greater than or equal to 10 times 73 or 730. So those conditions are met, and again, we already saw that all of the expected counts were in fact greater than 5, so all of our conditions are satisfied. Now we want to actually compute the degrees or the chi-square test statistic and the degrees of freedom. Again, I'm not even going to waste time going through calculating the chi-square test statistic by hand, but I do want to talk to you about how to come up with the degrees of freedom, because now we have two different things going on. We've got the day of the week, but we also have the two different groups. So what we'd want to do to find the degrees of freedom is multiply our row categories minus 1 times our column categories minus 1. And since we have 7 rows and 2 columns, my degrees of freedom for this problem would be, let's see, what is that, 6 times 1 or just 6? Okay. And so to determine what my chi-squared value is, I'm going to go ahead and quit out of that screen. So I'm back on my home screen. I'm going to go to Stat and Tests, and it might actually help to scroll from the bottom and scroll up. So you see that we're not going to choose the goodness of fit test this time. We're going to choose the other chi-squared test. And basically what it does, it's going to ask me where everything is. So I put my observed values in matrix A, and it's not asking me where the expected counts are, it's asking where do I want to put them. The calculator will actually come up with all the expected counts, and I want it to put them in in matrix B. So this screen, you really never have to change if you always put your observed counts in matrix A. And this gives me everything I need to write for my do statement. All right, so if we go here, what is the p-value? I'm basically saying the probability that chi-squared, notice that the chi-squared value is 6.549. We already said that the degrees of freedom are 6, and notice that the calculator will give that to you as well. And the p-value is 0.365. Okay, and obviously, since that value is greater than 0.05, the result is not significant. Okay, so we cannot reject our null hypothesis. And that means that we cannot conclude that the distribution of birthdays has changed from 1980 to 1993. And again, remember, we're not talking about a mean or a proportion this time. We're talking about the entire distribution. So you want to make sure you include that. So now, if you were asked to record all of your expected values, remember how I said it's so tedious, we don't really want to have to do it by hand, but they're listed in the matrix. If you go back to your matrix menu, so if you hit second and then X inverse, notice now matrix B is now a 7 by 2 matrix. Now under the names, if I scroll down to matrix B and press enter, actually, is it going to show me here? It'll give me matrix B. This is a little bit hard to see. It actually might be easier if you go back into this menu and go over to edit and then choose matrix B this way, even though you're not going to make any changes, it reduces the size of the values in the matrix and also does some rounding for you. So it's a little bit easier to see. But that now is your expected counts. And if we go back and compare that to the values that we did by hand, we might have rounded a few of those things a little bit differently, but obviously using the calculator is a lot easier. Okay, so in this particular example, we did not see a significant difference. So we'd be done. I mean, there would be no point in me going on any further because I've just concluded that I can't conclude that there's a significant difference, so I'm not really going to worry about it. However, if my p-value was small and there was a significant difference, I kind of want to figure out where that difference was occurring. So if you take a look, if you would go back to where's the thing where you can see them both? So if I were to go back and compare my observed counts to my expected counts, I might look for the biggest differences. And I think probably, didn't we say Thursdays seem to have, there seems to be a pretty big difference between what used to happen on Thursday and what's happening now. So if I wanted to do a follow-up analysis, I might do, for example, like a side-by-side bar graph where I'm comparing my observed and my expected counts for each of the different days of the week, or for the different groups, and seeing where the biggest differences occur, and then going a little bit further there with some sort of a write-up. Our focus today is just going to be on the test itself, and then we'll talk about the follow-up analysis a little bit later on. So let's talk about the other type of chi-square test. The chi-square test for independence is when we have two variables. We have one group of people and two different variables. But the chi-square test for independence is also something that is where your data is going to be displayed in a two-way table. So it's really important that you pay attention to that data and understand how many populations you're dealing with and how many variables you're comparing. Because as soon as you're dealing with two different variables, we're looking at a test for independence, and we're looking to see if there's an association between the two variables. So in this case, we'd be doing a test for independence. And so the way that really plays out in our test is how we set up our hypotheses. So if I'm doing a test for independence, my null hypothesis would be there is no association between the two categorical variables in the population of interest. Another way would be to say the two variables are independent. Right? Because if there's no association, that means the two variables would be independent. The alternative would be to say that there is an association between the two variables, or to say that they are not independent. I kind of like using the association instead of using the term independence because we're using independence in several different ways. When we're dealing with two completely different groups of people, we need independence. We need to make sure that we don't have anybody that's slipping into two groups. We need to make sure that we don't have an overlap. But when we're talking about two variables, we're looking to see if one variable is influencing another. So it's a slightly different way of looking at independence. So that's why I kind of like using the word association when we're setting up our hypothesis so it doesn't get confusing. The steps for the chi-square test for independence are identical to the test of homogeneity. So we're going to set up the matrices the same way. We're going to perform the test the same way. We just need to make sure when we're drawing our conclusions that, again, we're referring to independence or the association between the variables. So there is a slight difference in the random condition for the two tests. A test for independence uses data from one sample, but a test for homogeneity uses data from two or more samples. And in this case, the samples must also be independent. Oops. So anytime you're dealing with more than one group, the groups must be independent. But we also have independence between variables, and that's what we're looking at with this last test. So if we take a look at the example, it says chronic users of cocaine need the drug to feel pleasure. Perhaps giving them a medicine that fights depression will help them stay off cocaine. A 3-year study compared an antidepressant called disipramine with lithium, a standard treatment for cocaine addiction, and a placebo. The subjects were 72 chronic users of cocaine who wanted to break their drug habit. 24 of the subjects were randomly assigned to each treatment. The table below shows the counts and proportions of subjects who avoided relapse into cocaine during the study. So the sample proportions of subjects who stayed off cocaine are quite different. You can kind of see that, right? We have the same number of subjects in each group, but we can see that the number of subjects who relapsed, who did not relapse with the disipramine group seems much, much, much larger than those who had the placebo. So there looks like there's an indication that this disipramine drug actually may help with not relapsing. But we know that obviously every time we do something, we're going to see a little bit of a difference. So we need to know if that difference is significant in determining whether or not there's a relationship between these treatments. So the first thing we need to do is to create that two-way table of our observed values. And we need to be very careful because anytime we're doing a chi-square test, we are always dealing with the observed counts. And sometimes you're going to be given proportions, so you actually have to multiply it out. So we know what I observed is that 14 people in my disipramine group did not relapse. That means that 10 of them did. And in my lithium group, if 6 relapse, that means, if 6 did not relapse, that means 18 did. And in the placebo group, if 4 didn't relapse, that means that 20 did. And if I go ahead and put my totals down here, I've got 24, 48. There were 72 people total. And notice that this is one group of individuals categorized two different ways. I had a bunch of subjects and I categorized them two different ways. They are in different treatment groups and then they either relapsed or they didn't. And so this is a situation where I'd be looking for independence. I'd want to know if there's a relationship between the relapse rate and the type of treatment they received. Okay, so the matrix itself is what I'm kind of establishing here in these brackets. Those are my observed counts. If I wanted to create a matrix for my expected counts, this actually is something that's pretty simple to do by hand. Let me go ahead and put these numbers back in. So we had a 10 here and an 18 here and a 20 here. I know that, let's see, that of everyone, let's see, I had 24 out of 72 that did not relapse. And so if there's no difference between my groups and whether or not they relapse, so 24 out of 72. Oops, I'm doing this. I need to do this on my home screen, sorry. So 24 divided by 72. That works out evenly, doesn't it? It's a third. So a third of all my patients did not relapse. And so if there was no difference, if there was no association between the drug they took and whether or not they relapsed, then I would expect a third of every group to not relapse. And so if there were 24 people in each group, I would expect 8 not to relapse. And then I would expect, obviously, the other 2/3 would relapse. Since 2/3 of my entire group, if you think 48 out of 72 is 2/3. So overall, 2/3 relapsed and 1/3 didn't. And so if there was no difference between the treatments, I would expect the same ratio for each. Now, obviously, like I said, you don't have to do this by hand. You can absolutely do this in your calculator. So what I'd again want to do is go into my matrix menu. We're going to edit. And this is the number of rows is 3. The number of columns is 2. And remember, you're entering in the observed. So I'm entering in the 14, the 10, the 6, the 18, the 4, and the 20. And I'm going to go ahead and perform the test and then come back and just double check that the expected counts are what we expected them to be. So we go to Stat, tests. I'm again going to go up to my chi-square test, not the goodness of fit, just the regular chi-squared. It's going to ask me where my observed counts are. It's going to send my expected ones to matrix B. So I'm just going to hit calculate. This gives me everything I know for my test. Now I'm kind of doing this backwards because obviously we should be setting up our hypothesis and checking conditions. But if I go into my matrix now, into my second matrix, and I look at that matrix B, and again, I'm going to do it under the edit menu because it makes it a little bit easier to see. You can see that we were right in terms of the expected. So you do want to list your expected matrix on your paper because it helps you to verify that the conditions are met. So let's go ahead and write everything out that we need to for this test. So the first thing I'd want to do is state my hypotheses. And again, this would be that there would be no association between the type of treatment and relapse. Okay, no association. My alternative would be, I think there is. Okay. So the next thing we'd want to do is check our conditions. Remember, we have one group, but they were randomly assigned. So our conditions, we had random assignment. To the groups. Okay, I don't need independence here because I only had one group of individuals. I'm not comparing two different groups. One group. I can assume that my population of cocaine users, this is sad, that the population is at least 720. That's 10 times my group, 72. And again, we can see from the expected matrix that all expected counts are greater than or equal to 5. So all my conditions are met. This is now where you want to say, you know, all conditions met. We can proceed, and this is important that you write the correct chi-square distribution or the right chi-square test. We can proceed with chi-square test for independence. Okay. Now I can write my do. And if we go back, is it still on my home screen? I might need to do it again. So if we go to stat tests, all right, I've got the probability that chi is squared, and remember it's always greater than or equal to. In this case it's 10.5, and my p-value is 0.005. Make sure you include your degrees of freedom, which would be the number of rows minus 1 times the number of columns. So the number of rows were 3, the number of columns were 2, so it would be 2 times 1, which is just 2. And so the last thing to do then would be to draw conclusions about my test. And we can see very clearly that this result is significant. So since my p-value of 0.005 is less than alpha, the result is significant. We can reject the null hypothesis. We have evidence. And remember to go back to your alternative hypothesis. We have evidence to conclude there is an association between type of treatment and relapse. Okay. Now, what this test doesn't tell us, as much as you want to conclude this, it doesn't tell us which method is the best. Now, you can see from the naked data that the decipher-mean group seem to have the best results. That's not always that obvious. And so this would be a situation where, okay, so now that you found that this is significant, you'd want to dig a little bit deeper and figure out where those differences are occurring. So you might need to do a little bit of a follow-up with like comparing two proportions or comparing one proportion to a population. But the test itself just tells you if there's an association. It doesn't really tell you what is causing the association. So sometimes if you have a significant result, you have to dig a little bit deeper. Okay, and so and that's like the follow-up here. I'm not actually going to go through this. The follow-up analysis, it says the chi-square test is an overall test for comparing any number of population proportions. If the test allows us to reject the null hypothesis that all proportions are equal, we then want to do a follow-up analysis that examines the differences in detail. So for this, the cocaine study found significant differences among the proportions of successes for the 3 different treatments for cocaine addiction. We can see specific differences in 3 different ways. So what we could do is then we could look at the sample proportions. What do these values suggest about the differences in the treatment? So I could find the sample proportion of the people who didn't relapse in each of the groups, and then I could compare those. I could compare the observed and the expected counts a little bit deeper. What do these values suggest about the differences in the treatments? I could do this with like a double bar graph or a side-by-side bar graph. It also says that you could compare the individual distances between the observed and the expected counts that are added to get chi-squared. And so those would be all of the little values that when you add them up, they give you all the values of chi-squared. The calculator, I thought it gave you somewhere. Let me see one second. So I don't know if you remember this from our last lesson, but when you did the chi-square test for goodness of fit, and I just pulled this up on my calculator using one of the examples from last class, you can see on the calculator where it has that CNTRB, those are the values that combine to give you chi-squared. Unfortunately, it doesn't look like when we do a regular chi-squared test that our calculator puts that data anywhere, which surprises me. I always thought it did. So you'd have to kind of compute all of those individual values of chi-squared. We started to do that by hand a while ago, but you can, if you remember, it was very, very, very tedious. The very last thing I want to show you is what it looks like when you see like computer output. A lot of times on the AP exam, the question has more to do with your interpretation of the results than actually performing the test. So a lot of times you'll see a problem and then you'll see output from different computer software. And so this is an example in number 10 of a Minitab, which is a statistical software program, and what the output looks like when it's doing a chi-square test. So let's take a look at number 10. It says, are men and women equally likely to suffer lingering fear from watching scary movies as children? Researchers asked a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. The following table breaks down these results by gender. So we can definitely see that we've got some differences in terms of our numbers, but if you look, we also have a lot more women that we interviewed than men, and so we can obviously expect the counts in the women's section to be higher because we had more women that we were investigating or that we were questioning. So my question to you would be, what kind of situation is this? How many samples did we take? And if you look, it asked for a random sample of 117 college students. There was one sample, and we got 2 pieces of information from them. We got their gender, and we got whether or not they have these fright symptoms. Because it's one sample, and we've categorized these individuals in 2 different ways, we are going to be performing a test of independence. Because with independence, we're dealing with one sample. If I had a random sample of males and a random sample of females, and they were 2 completely separate groups, and they were both independent, then I could do a test of homogeneity. It's going to look the same in the table, though. Like, without reading the problem to see that it was a single random sample, I wouldn't have known that. So the math we do is identical. So in fact, you're not even going to have to do the math because you have in front of you the Minitab output. And so you have to read it carefully. We're looking at the chi-square test of males and females. The expected counts are printed below the observed counts. So these numbers here are your observed counts. These numbers here are your expected counts. These numbers here are the values that add to give you chi-squared. Okay, so the chi-squared contributions are printed below. And so notice at the bottom, you're told that chi-squared is equal to 4.028. So if I was to put this in like proper statistical notation, I'd be saying the probability that chi-squared is greater than or equal to 4.028. And here's my p-value, 0.045. And my degrees of freedom I'd report as 1. And so that's how I would write it out. If we were going to state the hypotheses, which I think is what you're asked to do first, remember if this is a test of independence, then I would say there is no association between gender and fright. Let's just and then my alternative would be there is an association. And then it says which type of test. We'd be dealing with a test for independence because we had one sample that we categorized in two different ways. So the conditions would be that we had SRS that was stated. We need to make sure that the population has at least 10 times 117. So we'll have to assume that. And then lastly, we need to make sure that all of our expected counts are greater than 5. So if I look at my expected counts, they are all greater than 5. Oops, expected counts are greater than or equal to 5. So all the conditions are met. And then when we conduct the test, again, this is where we're saying the probability that chi-squared is greater than or equal to 4.028 is equal to 0.045 with degrees of freedom of 1. And then we'd go ahead and state our conclusions. In this case, because if we set our significance level at 5%, I would say that the result is significant. I can reject the null hypothesis. We have evidence of an association between gender, and fright, or fright, how did they define it? Fright symptoms. So I hope you guys have a fabulous, fabulous, fabulous spring break. I'm not going to ask you to do any more than just take notes. If you want to get ahead of the game, obviously you can go and look at Chapter 11. When we come back from break, we'll do a couple activities and review and then test. And then we have one more section to cover in the textbook, and then we are done this course, and we will be able to spend, I think it's a solid 3 class periods reviewing for the AP exam. So my goal is to spend like a day going back over descriptive statistics where we were like doing histograms and modeling data, linear regression, and then a day going over experiments and sampling techniques, maybe do a little bit of probability, and then maybe a day just reviewing, maybe doing some practice testing. So have a fabulous break, enjoy yourselves, relax. I will see you when you get back.